Hey guys, this is chapter 4, and we're going to kind of go into the next set of definitions here. So when we're talking about solutions in chemistry, we want to be able to define the composition, because the composition, or how much solute to solvent is there, makes a big difference when it comes to reactions. So we want to be able to describe this. So in order to understand chemical reactions that happen inside solutions, you have to know the nature of the reaction. So this kind of gets back a little bit to those 5 types of reactions that we talked about last year in chemistry. So single replacement, double replacement, decomposition, synthesis, combustion, and redox. So that has to do with the nature of the reaction. Other things that might play in are like what kind of families are present. Is it going to be a nonmetal reacting with a nonmetal? Is it going to be a metal reacting with a nonmetal? What kind of ions do the reactants tend to form? What kind of compounds do the reactants tend to form? So that's why we do all the background with like the periodic table, because it helps us to predict these kind of things. The other thing you have to know in order to understand a chemical reaction that happens in solution is the amount of chemicals that are present. And that's where we get into the composition of the solutions. So we talked about this in class. These are kind of the definitions that describing the composition comes down to. Moles is a number of particles. Molarity is a number of particles per volume. Grams is your mass. And then density is your mass per volume. Now, like I said in class, the density in grams, you're going to end up using that if it's more convenient for you to measure your reactants and products, like on a scale. If you're going to measure out the amount of matter that's there in mass, then you're going to want to use grams and density. If it's more convenient for you to talk about the number of particles that are there, then you're going to use moles and molarity. Now, as chemists, when we're talking about how molecules change from the start of a reaction to the end of a reaction, the most convenient ratio that we have are those coefficients of a reaction. And those coefficients of a reaction are talking about the number of particles that you use. Those coefficients have nothing to do with the mass. And so as chemists, it's most convenient for us to use moles and molarity, which is why so much of our emphasis is going to be there. Remember that units for density are going to come out to be grams per milliliter, and units for molarity, oops, that was in the wrong spot. Maybe I'll put it on the other side. Okay, units for density are going to come out to be grams per milliliter, and units for molarity are going to come out to be moles of solute per milliliter or liter total solution. So let's move forward and talk about this a little bit. So this is just a super basic calculate the molarity kind of a problem. They give you the mass of solid NaOH. They give you the amount of the volume of your solution. Now, when you are using measurements to derive a different measurement, what I like to do is set it up as kind of the definition. So I know I want to calculate molarity. I'm going to break that down as much as I can in units. So molarity is made out of moles per liter. And do I have the things already given to me to calculate this? So I do have the volume of the solution, 1.50 liters of solution. Do I have the moles of my solute? I don't, but I do have the mass of my solute. So if you're looking at the mole hole, grams, moles, particles, number of particles, volume, and then you have the same thing on the other side. Okay, we are in mass of NaOH. We want to get to moles of NaOH. So it's a really simple calculation using molar mass. Let's do that. So we want to take 11, actually, let me do it sequentially, 11.5 grams NaOH. And I'm going to convert from grams of NaOH to moles of NaOH. So in 1 mole, it's the molar mass. So 1617 plus 22.9. All right, 17.008 plus 22.99 gives me 39.998. All right, well, let's go with 4 sig figs there, so it'll give us 40.00. All right, 11.5 divided by 40.00. I'm actually going to use second answer so I stay as accurate as possible. Okay, and that's going to get plugged in there. So 0.2875 moles of NaOH. Second answer divided by 1.5 gives me an answer of 0.19, and I can keep 3 significant figures, so 192 molar NaOH. All right, did you beat me there? I hope so. Okay, this practice we'll do together in class. So when you're talking about a solution's composition, we need to talk about how solutions are labeled. So when you go get a solution out of my back closet, if you get a solution, you're going to find liquid in a bottle, and that bottle is going to have a label on it. Now, the labels can be kind of deceiving. So let's say I have, it's labeled as 0.0 molar NaCl. Okay, now, does this tell me how much volume is in my bottle? No, it does not. It tells me the ratio between solute and the volume of solution, but it does not tell me how much solution is in my bottle. Second of all, what this means was when the solution inside the bottle was prepared, the ratio of solute, which is NaCl, by the way, to solution, so that is water plus NaCl, the ratio there was a 1:1, right? 1 mole of NaCl could have been put in the volume, and then water was added until the volume was 1 liter. Or 0.5 moles of NaCl was put into the bottle, and then water was added until the volume total was 0.5 liters. So we really don't know exactly how this was made, because what the label on the bottle communicates to us is a ratio, which can be great. Ratios are super helpful. We love ratios. But you have to know exactly what they communicate, right? The second way it can be kind of deceiving is when it says 1 molar NaCl on your bottle. NaCl is not actually present. What is actually present in the bottle? Pause the video and see if you can list as many things as you possibly can to what is present in the bottle. Okay, so hopefully you came up with a couple things. Water is actually present in the bottle. You dissolved NaCl into water, right? Also, Na plus is present in the bottle, and Cl minus is also present in the bottle. But NaCl, because it is a highly soluble salt, is not actually present even though it is labeled on the bottle. So you have to be careful with the label. The other thing that the label can tell us, which is not actually labeled, is what the ratios of these ions are. So if I have 1 mole of NaCl, and that gets dissolved and it falls apart into particles, what I now have is 1 mole of Na plus, and I have 1 mole of Cl minus. Okay, now this concept kind of throws people off because they're used to looking at a reaction in terms of kind of like an addition or a subtraction, but that's not what a reaction, actually tells us. A reaction communicates, okay, let's say purple is my Na, and let's say green is going to be my Cl minus. So if I count these molecules right now, what I have is I have 1 NaCl minus. Or if I'm talking about a macroscopic thing that I just weighed out, we can multiply this by Avogadro's number, and we can say that we have 1 mole of Na plus and Cl minus. Well, when this falls apart, notice I'm going to get Na plus by itself, and I'm going to get Cl minus by itself. So I'm going to get 1 ion of Na plus, or if I'm talking in terms of moles, I get 1 mole of Na plus. And I also get 1 ion of Cl minus, or 1 mole of Cl minus. Okay, so the reaction, don't let that throw you. You're just talking, it's not an addition, subtraction thing, right? You're talking about number of particles, and that's not always consistent. The mass may be consistent, but the number of particles is not consistent from the start to the finish, because if one molecule falls apart, now you have 2 things present. All right. Okay, so this is a perfect example of what we were just talking about. Now, if I'm looking at cobalt 2 nitrate here I have it. It tells you what you started with. You started with 0.5 molar of cobalt 2 nitrate. Now, what they want to know is what they're communicating to you in this information here is one way of displaying information. So part of chemistry and learning how to learn inside chemistry is organizing your thoughts, organizing what you have in the beginning and what you have in the end. With that in mind, let me introduce you to the ICE table. So I stands for initial, C stands for change, and E stands for equilibrium, which right now you can think of as the end. And a lot of times we're not actually going to communicate a true equilibrium here in chapter 4. We will get to an equilibrium chapter and we'll go through real equilibrium there. So for now, you can kind of assume that E means end. So what we have set up here, let me just kind of rewrite it for you so you can see where the numbers came from in this chart. Okay, so I'm going to rewrite this equation, CONO3, 2. So that's my reactant, and that reactant apparently is going to dissolve in water, and what I'm going to get is cobalt 2 and 2 nitrates. All right, so you can see my ratio here, 1 to 1 to 2. So my reactants to products, we have a similar situation that we talked about on the other slide. One thing falls apart into 3 things. One molecule falls apart into 3 ions. So if I have, all right, apparently in this chart, they have told you you started initially with 1 mole of cobalt-2 nitrate, 1 mole of cobalt-2 plus, and 2 moles of NO3 minus. Now, how would you know that you started with that? You wouldn't. They would have to tell you those were your starting amounts. Okay, I'm actually going to scratch this chart, this table that they've made, and we're going to make our own table because I feel like this table is not getting across the point that I want to get across to you. So let's forget this, ignore these numbers, and let's make up our own numbers and talk through this. Okay, so if I start with 1 mole of cobalt nitrate as a solid, and I put that into my solution, I'm going to say that I have started with 0 of my ions. I start step number 1, I put a chunk of cobalt-2 nitrate into my beaker. Step number 2, I fill my beaker with water to get the blessed thing to dissolve. So here we are. Initially, I had only solid cobalt-2 nitrate with no ions present. Then I added my water. So what is my change here? Well, if this is a soluble salt, then the definition of a soluble salt is it's going to fall apart completely, right? So I'm going to use all of my cobalt-2 nitrate. All of my cobalt-2 nitrate is going to fall apart into ions, and in the end, I'm going to have no solid cobalt-2 nitrate left because all of it will have fallen apart into ions. Okay, that's my premise. So if that's my premise, the question is now, how much of each ion do I have in the end? Let me change my color. Okay, so if I lose 1 mole of cobalt-2 nitrate, if 1 cobalt-2 nitrate falls apart, it's going to fall apart into 1 cobalt-2 plus ion. If 1 cobalt-2 nitrate molecule falls apart, cobalt, nitrate, nitrate. Okay, if 1 cobalt-2 nitrate falls apart, it's going to produce 2 nitrates. Okay, so what do I have left in the end? I have 1 cobalt-2 nitrate ion. I have 2 nitrates, or 2 moles. Okay, so that's pretty straightforward. However, what if I change my starting amount? We're going to do the same thing, only in starting with 1 mole, we're going to have a different starting amount. All right, let's say my starting amount now is 0.5. If I start with 0.5 moles of solid cobalt nitrate and no ions, and then I add water, how will this change? So let's say all my cobalt nitrate falls apart because we're assuming it's a very soluble salt, and I have no solid cobalt nitrate in the end. So I want you to pause the video here and see if you can predict. Can you tell me how many of each ion will be present when this reaction has taken place? So if I lose 0.5 moles of my cobalt-2 nitrate, I'm going to gain 0.5 moles of cobalt and gain double that, 2 times 0.5, which is 1.0 moles of nitrate. So in the end, here's how much of each of them I end up with. Is that what you got? Okay, so let's try it for, okay, before we try it for that, let's, I don't know if I want to introduce you to this yet. So in some cases, not all of the cobalt-2 nitrate is going to fall apart. And that would be called a slightly soluble salt. In the case of a slightly soluble salt, only part of the cobalt nitrate will fall apart. And so in that case, this change here will not be your initial amount. You would actually have a partial change there, and then you could figure out what you have in the end from that. But that is getting into equilibrium, and we really don't need to go there right now. We have a whole chapter that we can do on that later on in the year. So let's kind of stay with this simple, like, my whole salt is going to fall apart idea. One thing I do want you to do before we move to the next slide is I want you to take this amount and set it up in a reaction, write out the dissolving, the hydration reaction of iron 3 perchlorate, and then go ahead and tell me if 1 mole or 1 mole per liter of that falls apart, how much of each ion will I have in the end? Now would be a good time to pause. I'm assuming it's a soluble salt, so all of it's going to dissolve. And there you go. So if 1 mole per liter of iron 3 perchlorate falls apart, so that would be like iron, chlorate, perchlorate, if that all falls apart, I'm going to get 1 iron by itself and then 3 chlorates in the end. All right, so we're feeling more comfortable with this. Okay, so molarity. We talked about molarity being a ratio. Molarity is a ratio, and it relates moles of solute to liters of solution. Moles of solute to liters of solution. It's going to be a conversion factor. It has a unit on the top and the bottom. The top is going to be equivalent to the bottom. And so it can be used as a conversion factor. What is it going to convert between? What are the two things that will be on either side of this conversion? And hopefully you said moles and volume, right? So we have that on our mole hole already. Here it is. We have a conversion between moles and volume. Now, before this, we were using 22.4 liters per 1 mole, and that is the molar volume of a gas. That can only be used if you're talking about a gas. In this whole chapter 4 and then chapter 11, we're not talking about gases. We're talking about solutions. So you can't use this in solutions. If you want to talk about solutions, the ratio that you have to use to convert between moles and volume is molarity. Molarity is going to give you that conversion factor you need when you're talking about solutions. If you start with liters and multiply it by molarity, you'll get moles. If you start with moles, then you're going to have to flip molarity, put moles on the bottom, liters on the top, and then you're going to get your volume out of there. So a lot of the practice problems in your book are going to deal with this. Go through them. Go through them until you can do them from the start to the finish without any help, without any questions, without any reference. And once you can do that, then you are good and you can move on. I'm not saying don't use questions and don't ask questions and don't use references. Do that. But until you can do these problems without that aid, you need to keep practicing until you can do it start to finish. And then you need to check yourself. Can you do it finish to start? Can you do the problem backwards? Can you start in the middle and do the problem? Repetition is the key. Practice is the key. Okay, for example, here's a good example question. So how many moles of silver ions are present in 25 milliliters of 0.75 molar AgNO3? Okay, so if we look at where we are on the mole hole, okay, they have given us volume and they want us to get 2 moles. So we should be able to do this in one step. Starting with 25 milliliters. Excuse me. Okay, so remember, molarity is going to be moles per liter. So I can't multiply molarity times milliliters. I need to change that into liters. If you can change it without showing this calculation, do it. If you need to write out the calculation and make sure you're doing it the right direction, then do that too. Okay, 0.75 moles per liter. So your answer should be 0.01. Now I can keep 2 sig figs, so 19. And that's the liters is going to reduce, and I'm left with moles of AgNO3. Okay, now is that my answer? Nope, it's not, because you don't want moles of silver nitrate. You want moles of silver ions. Super important to label your work with the ions and compounds themselves so that you catch mistakes like this. Now, luckily for you, moles of AgNO3 to moles of Ag plus, if you have one silver nitrate compound, that's going to fall apart and give you 1 silver ion. And so your answer numerically will be the same, but you're going to have different units. Okay. And if it was not a 1-to-1 ratio here, you would not have ended up with the same number. So you got to be careful about what you're talking about. Okay. We're going to get into using this stuff in lab. And so you're going to start to see this term called the standard solution. So a standard solution or a standardized solution, also known as a stock solution, it's a solution whose concentration is accurately known. Now, if you were working for a for-profit lab, you would probably have bought your stock solution. It's cheaper for us to make it ourselves. So a lot of times I will make us a stock solution and then we'll use that as our standard solution and move forward. So if you see these 2 terms, that's what they mean. Okay, so here's a good example. If a chemist wants to analyze alcohol content of a certain wine, a chemist needs 1 liter of a 0.2 molar potassium dichromate solution. How much solid potassium dichromate must be weighed out to make this solution? So if you're weighing it out, you're going to weigh it out in grams. Okay, so let's look at the mole hole here. This little forky thing is just the other side of the mole hole, by the way. Okay, so they give us volume, they give us molarity, and they're asking us for mass. So we're going to have to go from volume to moles, moles to grams. Pause it and see if you can do that. Okay, and you should have gotten, let's see, we can use 3 sig figs. Liters reduces, moles reduce, and you're left with grams of dichromate. Okay, so our last concept in this whole idea of being able to describe the concentration of a solution has to do with a very specific alteration of the concentration. So when we're talking about altering the composition of a solution, you know, the easiest way to alter the composition of a solution is by putting in more solute, right? So if we have, let's say we have a solute and it has to do with sodium and chloride ions. All right, we have 1 liter of solution. We have 1 mole of NaCl. If we put more NaCl into our solution, obviously that's going to change the concentration in our solution, right? Let's say we put 1 more mole of NaCl into our solution. Okay, so we're going to go from 1 mole per liter, which is 1 molar, to 2 moles per liter, which is 2 molar. So that's one way we could change the solution and change the concentration of our solution. A second way we can change the concentration of our solution is through dilution. And lucky for you, you already talked about this a little bit. This is what we dealt with in lab 1 and lab 2. Half of the lab was dealing with creating these stock solutions, creating these standard solutions so we could create the standard graph, right? And we created these standard solutions by taking an original solution and adding water and diluting it. So dilution is referring to a very specific way of altering a solution. So it's kind of the opposite of what we just did on the right side of the screen with adding more solute. This is kind of the opposite. We're adding more water. So for example, if we start with our same 1 liter of solution, 1 mole of sodium chloride, we're going to have 1 mole per liter. It gives us a 1 molar NaCl solution, right? So what if I add more water without adding any more solute? So now instead of changing the numerator like I did on this side, what I'm going to change is the denominator, right? So I'm still going to have 1 mole of sodium chloride, but now I have 2 liters of my solution and my molarity decreases. Instead of the molarity increasing when you add solute, the molarity is going to decrease as you add water. Okay, so this specific scenario, number 2, is called dilution. And the catch here on the math is you are you're going to deal with, let me erase this side a little bit. Okay, so you really have like three things to keep track of. You have the solute, which is measured in moles, right? You have the molarity. Well, I guess let's list molarity third. Okay, you have the volume of your solution, which is in liters. And then together, those combine to make molarity in moles per liter. Okay, so molarity is a ratio like we talked about before. And these are the three things you have to keep track of. Now, the tricky thing about dilution is oftentimes you have the initial solution. You have the volume of water that goes in to your initial solution. And then you have, if this is initial, then you have a volume of water. And then you have a final solution over here. So you have three different volumes with three different concentrations, often three different volume measurements, and you have to keep track of which things match. If you're talking about the volume of your initial solution, that's going to correspond with the molarity of your initial solution. If you have volume of your final solution, it's going to correspond with molarity of your final solution, and you can't necessarily mix them. If you multiply your volume of your initial solution by your molarity of your final solution, you don't get anything meaningful, right? Whereas if you do volume times molarity of your initial, you're going to get moles of your initial. So you have to be very careful with what quantities are going with specific solutions. I find it really helpful to draw a picture of what's going on. So you can kind of, next to your pictures, you can write, okay, well, I know the volume of this one, I know the moles of this one, and you can kind of puzzle it out from there. The catch to this whole problem, the concept you have to wrap your mind around in order to really be able to be functional with dilution, is right here. Moles of solute before your dilution is going to be the same as moles of solute after your dilution. So that's how you get between the two calculations. Because if you can figure out moles for one, then you automatically have moles from the other, and you don't necessarily need to calculate it, right? If we're just adding water, like over here on the side, we're just adding water, we're not messing with the moles at all. So that is the key to all the math. If you can get to moles of one, you have the moles of the other, because moles doesn't change. Volume does, molarity does, moles do not. All right, for example, we need 500 milliliters of 1 molar acetic acid from 17.4 molar stock solution of acetic acid. What volume of the stock solution is required? Okay, so again, the crux of all of this is the moles that you take out of your stock solution is going to be the moles you put into your diluted solution, and then you add water. So we don't have the volume of the stock solution to get to moles of the stock solution, right? But we do have volume and molarity of our final solution, which we can get to moles there. So I'm going to go, again, molarity, remember, is moles per liter. So if they give you milliliters like they do here, you have to convert it into liters. So 0.5 liters of my final solution times 1 mole per liter of my final solution gives me 0.5 moles of my final solution. So in my beaker, somehow I need to get 0.5 moles. And that 0.5 moles is going to come from my stock solution, from some mysterious volume of my stock solution. So I'm going to now work from the volume of my final solution, from my moles of the final solution to moles of the stock solution. So this 0.5 moles comes from the 17.4 molar stock solution, and then we just kind of add water until we get to that desired volume. So now we go 0.5 moles that I'm taking, 0.5 moles in my final solution is going to be the same 0.5 moles that I took from the stock solution. So now I can go 0.5 moles of stock. I need moles on the bottom here. So 17.4 moles per 1 liter of stock. And that's going to get me liters of stock. Okay, so 0.5 divided by 17.4, 0.0287. 0.028, and I can keep 3 if my 500 milliliters is 3. 287, okay. So here's what's going to happen. Follow along on the bottom. I'm going to, from my stock bottle, I'm going to take 0.287, so 28.7 milliliters. I'm going to take that out and put it into a new beaker. 28.7 milliliters. And then I'm going to add water until I get to 500 milliliters. And then I will have the solution that I want, 500 milliliters of 1 molar acetic acid. Okay, dilution problems are a puzzle. The more you deal with the puzzle, the more this is going to conceptually make sense. So like we've talked about before, you have to work it forwards, you have to work it backwards, you have to start in the middle and work towards either end. The more sources you can see dilution problems from, the more these are going to make sense. Do them from our book. Go find them on ChemiBear. I can put Brown LeMay problems up if you guys want to see those. Go find them on a review book. Go to Khan Academy. Go find some random tutorial on Google. The more sources you can see this problem from, the more it's going to make sense. Now, there is a shortcut that I haven't told you about yet because I want you to understand the math behind it and not just use the shortcut without understanding why the shortcut works. So now that we've gone through all of that, let me show you the shortcut. Okay. So in this shortcut, you have to understand what it is and why it works and when you can use it. This is not a blanket shortcut that you can use anytime you're dealing with volume. This does not work for gases or liquids for that matter. It only works for solutions. It also doesn't work if a reaction is happening. It also doesn't work if you are adding solute. It only works for dilution because this whole equation comes down to a very special concept. So let me show you that. If I take, this is the M1V1 shortcut. Welcome. All right, so if I have molarity, moles per liter, and I multiply it by volume, liters, what do I get? I get moles of that first thing. And then if I do that again on the other side, okay, moles per liter, that would be volume, times, just kidding, that would be molarity, times liters, that would be volume. I'm going to get moles of solution number 2. And like I said, in dilution and dilution only, the moles you start with are equal to the moles you end with. So because this equation can be simplified to moles of solution 1 is equal to moles of solution 2, it gives you a framework to plug into and kind of simplifies your mental process. Now, you don't have to use this formula ever. You can do 100% dimensional analysis, 100% stoichiometry, and you never have to deal with this formula. It usually doesn't even save you time. It just saves you brain space, I guess. But you can very, very, very easily use it out of context. And if you use it out of context, you will get the wrong answer. It only works for dilution. Say that to yourself. It only works for dilution. Okay. So feel free to try M1V1, but I would only try it after you've really hammered out the concept through stoichiometry and you really understand the concept through stoichiometry. Then you can try a couple problems with M1V1. All right. That is it for today. Next time I see you, we'll come together and do some practice on this, and then we're going to get into the lab stuff. So you can look forward to that. Bye.